This question is about a compound X that contains both a ketone, which we know as a C-double bond O sandwiched between two carbons, and an ester, which we know is a C-double bond O R. So this is accounting for our three oxygens. We've got these two C-double bond O's aren't the same. C-double bond O, we've got ketone one and an ester one. And we've got our proton NMR shown below. We can see we've got 1, 2, 3, 4, 5 separate signals, 5 separate peaks, 5 different types of hydrogen, but 12 hydrogens altogether from our molecular formula. And then they've given us a table of information to help us. We can see the splitting patterns. So we can see that this one, if we look at it up at the spectrum, is a quartet. We're going to do some colouring. This one here, quartet. Then we've got this one, which is a triplet. And then we've got the next one, which is in a very similar location. So it's probably the similar type from the data sheet. It's also a triplet. It's not the same peak, but it's very similar. Then we've got this one here. It's a nice singlet. And then last but not least, we've got this here, which is another triplet. And the integration ratio hasn't been given us whole numbers. So that's an important thing to consider in a little bit. It says how many different types of proton? Well, how many different signals are there? How many different peaks? Even though some of them have been split, we can see that there were 1, 2, 3, 4, 5 different colours, 5 different peaks. And now it asks us what the whole number ratio is. And you might be tempted to just go, well, it's 8 to 8 to 8 to 12 to 12. Or you might want to simplify that. But we need to consider how many protons there are in total in this spectrum. So what I suggest you do is you go 0.8 to 0.8 to 0.8 to 1.2 to 1.2. If you add that up on your calculator, so 0.8 add 0.8 add 0.8, that's 2.4. Add 1.2, add 1.2, it comes to 4.8. Now go back up and look how many hydrogens are in the spectrum. So those 12 hydrogens in total. How on your calculator do you get from 4.8 to 12? If you type 12 divided by 4.8, you can see that you have to times by 2.5. If you times each of these numbers now by 2.5, you will get the actual number of hydrogens in each environment. So if you times 0.8 by 2.5, you'll find that you get 2 to 2 to 2 to 3 to 3. And if you add that up, it does come to 12. So the whole number ratio that we're working with here is 2 to 2 to 2 to 3 to 3. It must add up to give the number of hydrogens in the spectrum. So we might want to write that underneath, 2 to 2 to 2 to 3 to 3. It might be more helpful later on. Now we need to start to pull apart the information. So it's asking us about the peak at 2.2. So that was our singlet that we've coloured in blue. So if we just get the right colour pen. So this was our singlet, 2.2. And if we go to our data sheet, and we know we've got a lot of oxygen in here, it's this type. So we've got, it was a singlet. If we go back and just double check its integration as well, we can see we've now worked out it's a 3. We can put all the information together. So let's pull together all that bits of information and get our jigsaw piece. So the data sheet says it's an R with a C with a double bond O, and then it's a C next to that. Now, the integration 3 says there's 3 of this type. The singlet says there's no H's on the adjacent carbon, which seems sensible. There is no carbon to the right, and on the left we've got C-double bond O. It would be the end of the molecule if we put a H where that R group is, and we know we've got to have 7 HCs in this structure from our formula at the top, so we know that that's not going to be the case. That is what we've got from that first bit of information. Now we've got the next one, which is 4.13 and 1.26. So 4.13 was yellow, 1.26 was pink. Let's just go back and, so 4.13 was our yellow, 1.26 was our pink. 4.13 was a quartet, 1.26 was a triplet. So the exam board are telling us here that they want us to talk about what a triplet quartet tells us. And a triplet quartet, remember, is our clue. So triplet quartet equals ethyl, because you get a triplet for the CH3, it's being next to a CH2 makes it a triplet, and the CH2 being next to a CH3 makes its pica quartet. It does actually say about its chemical shift. So the 4.13 and the 1.26 is just the end of the chain, which makes sense because that would be this bit. It's if you need extra help to remember that the triplet doesn't mean it means it's next door neighbours, go back and look at its integration. It had an integration of a 3, and this one had an integration of a 2. So 3 hydrogens of the pink type that live next door to 2, causing the triplet. And then the 4.13 is telling us it's just outside of the region, but this has got to be it. The RC double bond O. So putting all this together, it's an RC double bond O. This is our ester group. So on the ester, we know that this is an ethyl ester. We don't know whether this CH3 is next to our ketone or our ester on the other side, but we know that the end of our ester is an ethyl group from that information. And now we've got the next bit. We've got 2.76 and 2.57. Again, the exam board are grouping them together, so it's telling us to look at the splitting pattern, which is triplet, both of area 2. So we've got 2.76, and then our other colour, which was the green at 2.57. They're both 2.76 and 2.57, the same type that this blue was before. So they're both of this type. But it's asking us about the splitting pattern, and the splitting pattern was that they were both triplets. So when the exam board tells you, think about the splitting pattern of these two, triplet equals CH2, CH2. It hasn't asked us in this question to do anything other than that, but if we were to look at the chemical shifts, they are both of the type that is next door to a C double bond O. So we know that the bit in brackets, it's not asked for, but we know from their chemical shift that that's what they are. Now we have to put all our jigsaw pieces together. My top tip is go find the CH3s. They're at the ends. So I'm going to start with my first piece of jigsaw from part C and say that's one end. I'm going to reverse that piece, put it on the left-hand side. So we had a CH3 next to a C double bond O. We had another CH3 here in part D. That must be at the other end of the molecule. So we had a CH3 that was next to a CH2 that was attached to an oxygen of an ester, like that. So these are the two pieces from from parts C and part D. And then in part E, we said sandwiched between two C double bond O's, there was a triplet part, CH2, CH2. Now we can double check. 1, 2, 3, 4, 5, 6, 7. 7 C's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H's, 1, 2, 3 O's, C7, H12, O3. Go back up, and we can see that that is what we were aiming for. We have got the ketone group here on the left and the ester group on the right. And if we just want to highlight things in to see what they might be, we can't 100% confirm every part, but we can see that the CH3 that was next to a C double bond O is here, and that the bit that led to the ethyl group, the yellow and pink, is here. Yellow protons here, pink protons here. Of these two, the 2.76 and the 2.57, it could be either way around. We have really no clues other than it's likely that the one that's 2.76, because it's a bit further in the numbers, it's closer to the more oxygens. So I'm going to colour that one in the orange colour, the one that's closer to the ester group, but it wouldn't make any difference which way around you had those.